Okay, finally, policy-based algorithms, those that policy gradient-based algorithms, provide us with another very, very powerful attribute, where they actually allow us to deal with continuous actions. And I want to discuss this next. So these policy-based methods are methods that use policy approximation. So they use approximation function for the policy. They actually offer a very practical way of dealing with continuous action space. So for instance, if we have an action for an autonomous car, for the steering that takes a value from the range -1 till 1, right? So any value in between those. Learning action values, for instance, just trying to train a Q network, is not practical in those cases. Why?
Because there's too many actions.
Yeah, you kind of have an infinite, maybe in the range, values for some action, and you can't learn for all of them, or you won't, right? It's not practical. So how can we train a policy to return any value between -1 and 1, for instance?
We could train
so we can train it. A simpler solution would just be to train a policy to update. You know, it takes a state and it returns an action, a continuous action. No problem. A deep neural network can fit any continuous action to arbitrary precision. So it can just output a value. But then, right, we'll have a problem with that will be a deterministic policy. It gets a state and returns an action. As I said before, we will see one actor-critic approach that uses deterministic policies. But in most cases, we want to have a soft policy. Or many of the algorithms rely on a soft policy. So it's actually pretty easy to define a policy function that returns a regression policy, right? That returns some value in a continuous range. But I want to define a soft policy. How do we do that?
We learn a distribution.
We learn it, right. We want a policy approximator that outputs a distribution. So we want to learn a probability density function. So instead of a soft policy that takes an action and a state and returns a probability, for instance, maybe using a softmax over the state, and then you have a distribution over all of the actions. So softmax works with a discrete, actually it can work on a continuous set of actions, but for what we've seen before, if we want to have an output, a specific score for each one of the actions, then it requires a discrete set of actions. But now we want our policy to take a state and return a probability density function over all of the actions, or over a continuous dimension of the action. Okay, so let's see a simple example that is actually used in many algorithms. It's a go-to example for a PDF, which would be to use a normal distribution or a Gaussian. Right, so let's assume that our policy is defined by a Gaussian PDF over continuous actions. So this is just the definition of a Gaussian, right? If you don't remember it, hopefully you do remember it. This is just a Gaussian that is defined for a specific value, input value. It provides the probability based on the mean and the standard deviation belonging to the specific Gaussian, right? Which we can see here on the left, different Gaussians with different mu's and sigmas. The mu and sigma defines the Gaussians. By the way, a Gaussian does not have to be on a 1D plane, right? On a 2D plane. Sorry, this is considered a 1D plane. What will happen if we want to define a Gaussian over higher dimensions?
We just have a lot more means and standard deviations.
Right, mu becomes a vector.
Yes.
Right, and sigma becomes
also a vector.
It becomes a matrix actually, covariance matrix. The variance becomes a covariance matrix. But yeah, so for a multidimensional Gaussian, these are defined by a mu vector and a covariance matrix. Okay, not to be confused, by the way, in this definition here, it uses pi. Sorry for the abuse of notation, but I colored it red, just not to be confused with the black pi. So we use pi for a policy, but for a Gaussian, we use also the constant pi. I just colored it red, so you won't get confused. I'm sorry for that, but this is just the notation used in the literature. So now we can define our policy based on some sigma and some mu. And our policy will output some value, some continuous values that is drawn from the Gaussian. What are the tunable parameters for such a policy?
The mean and the standard deviation.
Yes, this is what we want to try and define correctly. We want to have the best mean, the best standard deviation in order to get a good policy. Policy that maybe has good performance and sufficient exploration at the end of the day. So indeed, the mean and the standard deviation for each state would be approximated using our function approximator. We can use, we use the function approximator to do those. Mu would be a function of some tunable parameter, let's say theta mu, right? And so our approximator will return some value, which will, for each state, it will output the mean value using the approximation, our mu approximation. And same goes for sigma, using a different set of tunable parameters. By the way, for efficiency, usually you want to have those two represented in the same network, just with two different heads. One head for mu and one head for sigma. Why is that? Because mostly they rely on the same high-level features that are learned with the deep neural network, right? And you just need to, at the end, at the final layer, maybe compute them slightly differently. But the state, the high-level state should be mostly the same for both of them, for making the correct decision for both cases. Okay, so how can we update the PDF? We want to update our policy over time, right? So we approximate, just for the notation, we approximate mu using theta mu and approximate sigma using theta sigma. As I said previously, they might have a lot of shared values, and that's okay. Then you update any shared parameter using both gradients, that's fine. But for the sake of the more general presentation, I'm just calling them, assuming that these are different. Again, for practical cases, you don't want to keep them different. Then you just update them with the two gradients. Okay, so our policy is now defined over all of the tunable parameters, where sigma is obtained for the given state, given our tunable parameters for sigma, and mu is obtained for the given state, given theta mu. Can we compute the policy gradient? I mean, that's what we want to do, right? The policy is defined by both the mean and standard deviation, and both need to be updated over time. But in what direction? In what direction? Well, in the policy gradient direction, right? But what is the policy gradient for this? Previously, we computed the policy gradient just for the probability of a given action in a given state. And we assume that our network produces those probabilities. But now that's not the case. Our network, our approximator produces a distribution. How can we update that distribution? And of course, it depends on the exactly parameterized distribution. Sigmoid Gaussian is a parameterized distribution. What do I mean? It's a distribution that is defined by two parameters, the Gaussian. By the way, there are many parameterized distributions that might be defined with more parameters. Beta, F distribution, log norm, I don't know, there are really many of those. So this is a specific example for a Gaussian, but the gradients that I'm producing should be extendable to other distributions. Okay, so the direction that we want to update is, of course, using our policy gradient theory. We want to take the advantage function and multiply it by the gradient of the log pi, the log probability of action A at state S. what is the log probability for this? So we'll have to do some math.
Yeah.
Okay, so let's do some math. So let's look at the probability for that is defined by a policy which is represented by a Gaussian. And of course we'll have to compute the derivatives for the Gaussian. We'll use the chain rule, and then we'll send those derivatives back to our approximation for our mu and sigma approximation. Okay, so in order to derive the derivative of the Gaussian, right, we're going to use several known rules, known gradient rules. Right, we're going to use the product rule, we're going to use the chain rule, and we're going to use the gradient of an exponent rule. I'm not sure if there's a specific name for that. Okay? And now you can just use these three rules, and you can easily compute the gradient with respect to mu, right, for our network parameters, right, for approximated parameters. You'll see this here. Right, using the chain rule, you just see we multiply here at the gradient of the deep neural network, for instance, for approximating mu, times this is the gradient, this portion here is the gradient in the Gaussian with respect to the mu value, right? And again, I won't do all of the math, but you can easily see that this results from the Gaussian. With respect, this is the derivative with respect to mu. We do the same for sigma, okay? And the gradient of the Gaussian with respect to sigma is exactly this. Again, as a homework, please do the full derivation. Again, I provided all of the exact rules that you need to use, and I'm sure you'll be able to arrive at the same solution, but you're more than encouraged to do so. Okay, and now we can define the policy gradient for a Gaussian that is updated using the policy gradient theory, right? For a continuous action dimension. This is a specific dimension. So you might have, I'm saying action dimensions because you might have the case where you have many action dimensions, where some of them are discrete and other are continuous, and you might need to do different tricks for updating each one of your dimensions. Don't worry about that too much for now, because it's you'll be able to figure it out if that will be the case for you. So now we can define exactly the policy gradients for a Gaussian. And what does that mean? So for instance, if we sample an action in a specific state and it yielded a positive advantage, what do you mean yielded a positive advantage? I don't know, we passed it through our approximation and we found that it's probably better. Or given our current approximation, it looks like this action is better compared to the action produced by our current policy, mostly. So currently our policy would mainly like to use action 0, right? So the blue line is our current policy, so usually it takes the action 0. Or in expectancy, it will take the action 0. And now we sampled an action that is minus 1.8, and we actually saw that it's a good action to take. So now we want to push our policy towards the new action. How will we change mu and how will we change sigma?
We'll reduce mu.
Reduce mu, yeah, that's correct.
Increase sigma.
And increase sigma, right. So you'll have to look at each one of those separately. If I'm just updating sigma and I want to have higher probability of taking this action, just looking at sigma, I have to increase sigma, right? In order to have higher probability of sampling this value. If I'm just looking at mu, I have to decrease mu in order to get higher probability of obtaining this value. And by the way, this is the definition of partial derivatives. It's just how do I just change this parameter in order to increase the value, right? Question, yeah.
Is it possible to just have a constant sigma?
Ooh, yes. A constant sigma would probably work, but then you can use other tricks. A constant sigma is usually what we use for deterministic policies, but still ensuring some exploration. If you're using policy gradient while assuming the Gaussian, so normally it would be beneficial for you to update both sigma and mu. Especially, so sigma, you can see here that increasing sigma will be beneficial when? In what cases? When you want to do more exploration, right? So, changing sigma or having a dynamic sigma might be very useful in many cases, specifically in initial stages as you want more exploration, and you later allow it to reduce as you want less exploration and maybe to converge on the specific action, convergence on the mu. And we'll discuss those later. We'll discuss approaches that actually try to play with the sigma and to get some target distribution or target exploration, where we would like to explore more, and maybe other approaches that use a constant sigma that might hurt exploration though. Right, but they can use other tricks. We'll see actually both of these approaches later on. Okay, so indeed we increase sigma and reduce mu. Move our policy accordingly.